Welcome to the class of Control System 2. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today we will discuss on obtaining the characteristic equation and the transfer function from the state variable model. In your today's lecture, the contents are the characteristic equation from state space, the transfer function from state space, state variable formulation from signal flow graph, transfer function from state model, the transfer function and state model using the MATLAB, and the reference with the MCQ questions. So first is the characteristic equation. Actually, the characteristic equation or the characteristic polynomial is the equation which is solved to find out the roots of the system. And the characteristic equation in a variable can be determined as determinant of a minus lambda I equal to 0. As the right hand side is 0, so we can write down in the same way determinant of lambda I minus a is equal to 0, where a can be defined as the system matrix, and this a can be calculated from the state equation of the given system. So if a is a k by k matrix, then we can write the elements of the A matrix in this manner: small a11, a12 up to a1k, and similarly column wise a11, a21 up to ak1. So determinant of the a minus lambda I becomes a11 minus lambda, and the diagonal elements are a22 minus lambda up to akk minus lambda, and the remaining elements are same because the I represents the identity matrix. So first, to find out the characteristic equation, we will calculate the determinant of Si minus a, or the lambda I minus a, or determinant of a minus lambda I. Then we will compare it with the 0. Then the equation which we have get, that is known as the characteristic equation or the characteristic polynomial of any given system. Next is the characteristic equation from the state space. So here we can see that one system is given, and the system is represented by x1 dot, x2 dot equal to minus 2, 4 plus 2 minus 1 into x1, x2 plus 0, 1 into ut. So here this one is the state equation, and the system matrix or A matrix is given as minus 2, 4 plus 2 minus 1. So to find out the characteristic equation, only the system matrix is sufficient. There is no requirement of the knowledge of the B matrix or C or D matrix. So first we will put the value of A matrix, and then we will find out the equation by putting the values of A in determinant of lambda I or Si minus A, and then compare it with equal to 0. So if we put this Si minus A, then this identity matrix will be have the same order of the system matrix A. Now this A matrix is 2 by 2 order. So that means the identity matrix will be 1 0 and 0 1. So then we will multiply S with it. So it will be S 0, and in the next row it will be 0 S, and then we are subtracting this Si minus A. So it becomes S plus 2 and 0 minus 4, which gives us minus 4. Here it is 0 minus 2 gives us minus 2, and here it is S minus of minus 1, that gives us S plus 1. Now the determinant of this can be found out. S plus 2 into S plus 1 minus minus 4 into minus 2, which gives us minus 8. So S square minus plus 3S minus 6 equal to 0 is the characteristic equation of this given state model. So next, if we want to find out the roots of this characteristic polynomial, then we can use the Sridharacharya formula and we can find out the roots of this characteristic equation, or we can find the roots or poles of the given system. Next is the transfer function from the state space. So for the linear time invariant system, we know that the state model can be represented by two equations. One is the state equation and another is the output equation. So the state equation is x dot equal to ax plus bu, and y is equal to cx plus du is the output equation. Now the transfer function is denoted as the Laplace transform of output divided by the Laplace transform of input, assuming all the initial conditions are 0. So the transfer function model is in the frequency domain model, whereas the state model is in the time domain. So to change the time domain into frequency domain, we have to apply the Laplace transform on the both sides of the state equation as well as the output equation. So first consider the state equation x dot equal to ax plus bu. So it is in the time domain equation. So after applying the Laplace transform in this equation, we get s into xs equal to a into xs, the Laplace of x becomes xs plus b into us. Or we can take x as a common. Now s is the operator and a is a matrix. So we have to multiply the identity matrix to perform this subtraction. That means this Si minus A into xs is equal to b into us. Similarly, we can find out the x's value from this equation, and x's becomes the Si minus A inverse into bus. So next we are going to apply the Laplace transform on the both sides of the output equation. So output equation is y equal to cx plus du, and if we apply the Laplace transform, so y becomes y of s and c into xs plus d into us. Or we can put the value of xs, which is Si minus A inverse into bus in the case of xs over here, and the ys becomes c into Si minus A inverse into b into us plus d into us. Now we can take common the us. So it becomes c into Si minus A inverse into b plus d. Now the transfer function has been defined as the ratio of the Laplace of output, and output here it is y. So Laplace of output is ys to the input Laplace transform, and input is here u. So Laplace of input is us. So Ys by Us at the zero initial conditions represent the transfer function of the system. So that's why, as we have taken this Laplace transform and directly assume that all initial conditions are zero, that's why this Ys by Us represents the transfer function of this system, and it can be found out by the relation C into Si minus A inverse into B plus D. So as in the maximum cases, D becomes 0, which is the input-output coupling matrix, and the direct coupling of the input to the output is very rare in the control system. So Ys by Us can also be found out by using the formula C into Si minus A inverse into B. Next is the state variable formulation from the signal flow graph. Here one signal flow graph is given, and in this signal flow graph 3 integrators are there, and integrator means the Laplace transform of the integrator is 1 by S or S inverse. So each S inverse term represents there is a presence of one integrator, and signal is flowing from the left to right, and the input of this signal is the ut and output of this system is y. So to find out the state variable formulation from the signal flow graph, first we have to assign the state variables. Now the number of state variable will be dependent upon the integrating term. So there are 3 number of integrators present in this signal flow graph. So the order of this system will be 3. So we have to check the 3 state variables. So first, from this diagram we can see that x2 is going to this x1, and s1 s to the power minus 1 is written over here. That means x1 is obtained by integrating this x2. Similarly, x2 is obtained by integrating the x3, and x3 will be obtained by integrating the x3 dot. So from this graph we can say that x2 is equal to x1 dot and x3 is equal to x2 dot, because after integration of x3, x2 has been obtained. So we can write x1 dot is equal to x2 and x2 dot is equal to x3. Similarly, the x3 dot can be written as, for this node we will consider all incoming signals and outgoing signals from this. So the incoming signals are u of t minus this 2 is coming from x3 node. So minus 2 of x3 minus 3 feedback that is coming from the x2 node. So minus 3 into x2 minus 4 into x1. So we can write the equation at different nodes in the state variable form. So x1 dot becomes x2 and x2 dot equal to x3 and x3 dot is equal to u minus 2x3 minus 3x2 minus 4x1, and the last one is the output y, and that is equal to 1 into this x1, because 1 is the transmittance over here. So from these 4 equations we can write the state equation and the output equation from the general form of the state equation and output equation. So now the general form of the state equation is x dot t is equal to a into xt plus b into ut, and the general form of the output equation is yt equal to c into xt plus d into ut. So here, as there are 3 number of integrators, so 3 state variables has been chosen. And these three state variables are x1, x2 and x3. So here this is the x dot, that means the first derivative of the state variable. So x1 dot, as x1, x2 and x3 are the state variables, so this matrix will be x1 dot, x2 dot and x3 dot, and that is equal to, this one is the A matrix or the system matrix, and it will be n by n order. That means as there are 3 number of integrators, so n is equal to 3, or the order of this system is equal to 3. So the A matrix will be a 3 by 3 square matrix into x. So x is equal to x1, x2 and x3 in vector matrix form, plus b into u. As it is a third order system, so B matrix will be 3 by 1 matrix. So this matrix is B into U, and Y is equal to C matrix. Similarly, C matrix will be 1 by 3 in case of third order system, plus D into U. Now, how to write the coefficients? So the position 1, 1 represents the coefficient of x1. The 1, 2 position represents the coefficient of x2. 1, 3 position represents the coefficient of x3. And for this is same for the remaining x1, x2 dot and x3 dot also. So for the first one, x1 dot is equal to x2. So the coefficient of the remaining will be 0. That means x1 dot can be written as 0 into x1 plus 1 into x2 plus 0 into x3 plus 0 into u. In the same way, we can write that x2 dot, that is equal to x3, or it can be written as 0 into x1 plus 0 into x2 plus 1 into x3 plus 0 into u. And x3 dot, for x3 dot the coefficient of x1 is -4, for x2 it is -3, and for x3 it is -2. So -4, -3, -2, and for u the coefficient is 1. So that's why the B matrix, it is 0, 0 and 1. Similarly, we can find out the Y matrix from this equation. Y is equal to x1, and if x1, coefficient of x1 is 1, so for the rest of the two, the coefficients are 0. So y is equal to 1, 0 and 0, and for u it is also 0. So this one is the system matrix 0, 1, 0, 0, 0, 1, -4, -3, -2. The B matrix is 0, 0, 1, column matrix. C is always the row matrix, that is 1, 0, 0, and D is here null matrix. So in this way, we can formulate the state variable form from the signal flow graph. And the same formula is we can apply for the case of block diagram also. Next, take an example to determine the transfer function from the state model. So here one state space model is given as x dot, that is equal to x1 dot, x2 dot equal to -1, -1, 1, 0, x1, x2 plus 1, 0, u, and y is given as 0, 1, x1, x2. So D is not present. So from this state model, we can easily identify the system matrix, the input-output coupling matrix, the input coupling matrix, and the output coupling matrix. So the system matrix is -1, -1, 1 and 0. The input coupling matrix or B matrix is equal to 1, 0. The output coupling matrix or C matrix becomes 0, 1, and finally the D matrix or the input-output coupling matrix is equal to 0. Now, if we recall the formula of the transfer function, then Ys by Us at all initial conditions are 0 can be expressed as C into Si minus A inverse into B. So C matrix is given. We just have to find out the Si minus A inverse. So similarly, as A is a 2 by 2 matrix, I will be identity matrix of second order. So it will be 1 0 0 1, and when it is multiplied with S, then it will be S0 0S, and then we will perform the Si minus A, and it looks like S plus 1 1 minus 1 and S. Then we will find out the inverse of this matrix by using the formula cofactor of this Si minus A divided by the determinant. So the determinant of S plus 1 1 minus 1 and S matrix is this one. So then we will multiply this B with this matrix, and then it will be multiplied with this C matrix. And we will remember that in case of matrix multiplication, B into C is not is equal to C into B matrix. So the transfer function Ys by Us can be obtained as 1 divided by this A square plus S plus 1. Now this S square plus AS plus 1 has been obtained from the formula determinant of Si minus A, and this one is the characteristics equation of the given state model. So just using the formula Ys by Us equal to C into Si minus A inverse into B plus D, and as D is equal to 0, we have eliminated the D part. So we can find out the transfer function from the state model. Next is the transfer function and state model using the MATLAB code. So here for an example, one transfer function is given, and the transfer function is represented by the GS, which is the ratio of the output Ys and the input Rs. And this transfer function is given as 2s square plus 8s plus 6 by s to the power 3 plus 8s square plus 16s plus 6. So we can obtain this state space representation by the SS function, and the state space representation of the system can be obtained as follows. So the MATLAB code is numerator. So first we will identify the numerator and write the coefficient of the numerators. So the coefficient of the numerator is 2, then 8, then 6. Similarly, we will identify the denominator, and this denominator is 1, that is the coefficient of s to the power 3, then 8, then 16, and then 6. So we will write the numerator and denominator. Then the system transfer function, we can give it g over here also. This is just a name, and that is equal to transfer function num comma den. And if we write then system underscore the ss equal to ss of system transfer function, or whatever name we will give here. Suppose this is given as g, then ss of g, then the A matrix will be this minus 8, minus 4, minus 1.5, 4, 0, 0, 0, 1 and 0. Similarly, the U matrix will be the B matrix equal to 2, 0, 0, which is a column matrix. The C matrix will be a row matrix, that is 1, 1 and 0.75, and D becomes 0. So this is the continuous time model, and the transfer function after entering this system transfer function is equal to transfer function of num comma den. The answer of this command will be like this: 2s square plus 8s plus 6 by s to the power 3 plus 8s square plus 16s plus 6. So in this way we can use the MATLAB code to define the transfer function and to obtain the state model from the given transfer function. These are my references. So after this video lecture, I hope that you have got a clear idea about the today's topic, the eigenvalues and the eigenvectors. Now we will go through some question answer session in context of this video lecture, and you are requested to go through it gradually and solve by your own. The answers are attached at the end of each question.